So in this video, we'll be going over the Keplerian rotation curves and seeing how these form a basis of evidence of dark matter. So um, essentially what we're going to be doing is looking at a galaxy and looking at how the velocity of objects orbiting this galaxy um, should change with distance. So if this is a galaxy here, um, and you have an object orbiting it a distance r away, we know from Newton's law that F equals ma, and since this object will be going in a circular path, we know that the acceleration will be a sub c, where that is the centripetal acceleration. So this equals mv squared over r. We also know that because the only force on this object is due to the mass inside it, we can say that this equals g at big M little m over r squared, where m is sort of the collective mass that is pulling it inside. So like it's basically the mass enclosed by this radius. So if we solve this equation, we get v equals the square root of g m enclosed over r. Now we'll notice that when r is when r is just bigger than the radius of the when r is bigger than the radius of sort of the galaxy, or where all the mass is concentrated, that this mass enclosed is just the total mass of the galaxy. So we have for r bigger than big R, v equals g m total over r. However, when r is less than big R, so when our object is sort of inside the mass distribution, it becomes slightly more complicated. So we know that due to the shell theorem, only the mass inside, or only the mass enclosed by this object will be exerting any net force on it. So what we're really interested in is this mass enclosed, the mass enclosed in green. So if the total mass of the galaxy is m tote, then mass enclosed is just m tote times the ratio r to big R cubed. It's just the the volume, the ratio of the volumes, because we're assuming the density is constant. So if we take this expression and we plug it in for m enclosed up here, we'll get that for r less than big R, v equals square root of g r little r cubed over big R cubed divided by r. So then we can simplify this to, we can pull out an r because this cancels, this is r squared. So we get r times g m total, gm total over big R cubed. So basically what we've sort of figured out is that the velocity of an object outside of a galaxy is proportional to r for r inside the mass distribution, and it's proportional to 1 over the square root of r for r bigger than, or for r outside the where the mass is distributed. So if we were to graph this on a on the xy plane, we notice that what we're going to get is a linear curve up to R, up to big R, but then after that it's going to start to decrease and be proportional to this to 1 over the square root of R. So that is what this analysis tells us. However, when we actually observe objects in the universe and we look at their velocities, we notice that up until R, it follows the Keplerian path that we expect it to. However, after R, and so for like distances way outside the galaxy where there's very little mass, we expect it to start to drop off. We expect the velocities to decrease, but in fact, they don't really decrease at all. Instead, they essentially remain constant, which implies that one of our assumptions is not correct, namely that the mass is not all concentrated inside this radius r, that there must be mass that we're not seeing, or mass that is somehow affecting the gravitational force outside the central mass distribution. So sort of the only thing that can explain the fact that that it's not behaving like this is if this term is different. So if v is not proportional to 1 over square root of r, the only thing that can possibly be not what we thought it was is the total mass enclosed. And so if what we thought was that v equals the square root of gm over r, but in reality, v is not dependent on r at all, but it's constant, then we know that the mass must somehow depend on the radius. So we can say essentially that c equals square root of gm of r over r, which implies that cr squared, c squared divided by g equals m of r. So basically we know that this mass distribution, sort of the mass enclosed, actually increases linearly with r. So when we graph the observed mass of the galaxy versus distance, we notice that most of the mass is concentrated in radiuses close to the center. This is also known as the central bulge. This is where you'll find most of the mass of the galaxy. It's sort of the highest mass density. So when you contrast sort of what we see with what we expect based on our analysis, there ends up being a big difference. There's a big gap in the expected versus observed. And sort of, the way we explain this is sort of through the kind of a theoretical construct of dark matter. It's matter that we can't see, that we can't observe, but we know that it is there and that it is affecting, well, we at least know that it is affecting visible matter. And in fact, dark matter if it exists, affects or is like much more plentiful than visible matter, as we can see from this chart. If we accept the notion of this construct of dark matter, we'll be led to the conclusion that most of our universe is in fact made up of it, rather than matter that we are kind of used to, like atoms and baryonic matter.